My name is Jolie Nelson, and for my final project for computer security, my presentation will be on a summary of security risks of machine learning. Machine learning is the study of computer algorithms that improve automatically through experience. By looking at data, they're able to learn some model to describe that data. And there are a number of important assets that we want to protect. The first is the model itself. A lot of effort goes into designing, training, and deploying the model, and we want to protect that from adversaries who want to steal that model. Another is the data. There could be private data involved in the training, the testing, and any live production of the model, and we want to protect that from adversaries. We want to keep that data from being leaked. A third asset is the integrity of the model output. We want to make sure that the model is giving good predictions, even if it is encountering an adversary, especially if that model's output is being used to make critical decisions. Like any technology, there are security risks associated with machine learning. Some are not exclusive to machine learning. So machine learning requires a lot of data. There's just an inherent security risk to storing lots of data. When you have a lot of data lying around, there's a high probability that bad things can happen to it. Machine learning is a relatively new technology. Vulnerabilities are not well studied in production, and people are just very excited about deploying it, and they might not be as focused on security. But there are some security risks that are more exclusive to machine learning, and these are going to be the types of risks that I'm going to be talking about in this presentation. So the first one are model extraction attacks. This is when an adversary reverse engineers and steals a model. Second are model inversion attacks. This is when an adversary uses the model to leak information about the training data. And the third are adversarial example attacks. And this is when an adversary feeds in data that leads to incorrect model predictions. So the first attack we're going to talk about are model extraction attacks. And this is where an adversary reverse engineers a model that's been made available to query. And by doing this, they're able to replicate the model for themselves. So here we have an example of a vulnerable model. This model takes in text data and it outputs a class for that data. So in this case, it takes in some text and it outputs the sentiment associated with that text, whether it's positive or negative. So how this attack works is when attackers send a large number of queries to the model to get back labels. These queries don't need to make sense. They can just be gibberish. So like in this example here, we have an adversary. They're sending in this text that doesn't really make sense. They're sending it in the model and they are getting a label for it. So basically what the adversary is doing is they're labeling their queries, and now they can use those labeled queries to train their own model. And even if they don't have the exact same underlying architecture, they basically can use that model that they've extracted to achieve their goals. So why might an adversary want to extract a model? Well, one of the reasons might be theft. They just want to stop paying for the API and launch a competitor. And by reconstructing the general behavior of the model, they can do that. Another reason might be reconnaissance. Stealing the model can be a stepping stone for other types of attacks. Having that copy of the model, and even if the architecture of the model isn't exactly the same, it still makes model inversion attacks and generating adversarial examples much easier. So what are some possible defenses for this? Well, one of the things we could do is try to detect queries that could be part of a model extraction attack, and we could block those queries. But this isn't very robust. Attackers can find ways around this. Another possible defense is perturbing the output. So basically what you do is you do some extra calculations to vary the output of the model. So not giving it exactly what the model's prediction is, you do an extra calculation to change it a little bit. Depending on the model, there may be some ways to reduce an attacker's accuracy while keeping the original model's accuracy pretty high. The papers that I saw that talked about this, there was a lot of complex math. I don't really want to go into it. But it's a really cool area of research. It's relatively new. Most of the papers that I saw on this had been published this year. So I'm really excited to see how this area develops. So the next attack we're going to talk about is model inversion attacks. And this is when an attacker uses the model to leak information about the training data set. And to do this attack, the attacker doesn't need the data set. They just need to be able to query that model and get some kind of output from that model. So this works by the attacker querying the model by giving it some input, and then they receive some output about their query. So if the model is a regression model, which means that it predicts a numerical value, they might see that numerical value that gets predicted. If the model is classification, they might receive a confidence score that their input is of a certain class. So like, I'm 75% sure that you've shown me a picture of a cat. Then the adversary will use that output to estimate if the input they gave it might be from someone in the model. The specifics of this attack depend on the type of model. We're going to be talking about it in a context where it's used in a facial recognition neural network. Okay, so say that we have an attacker that has access to this facial recognition model that takes in images and outputs who it thinks that person is with a confidence score. So here we've given the model a picture of someone's face.png, and it outputs that it is 55.9 blah 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 % sure that this face belongs to Alice. So basically what an attacker can do is that they generate a lot of faces and they check the confidence scores, and then they can use that to generate better and better faces. And they use gradient descent to do this. So gradient descent is an optimization algorithm for finding a local minimum of a function. In our case, our function's input might be the various parts of the image, like maybe the individual pixels, and the output is the confidence score. And basically what we do is we use gradient descent to find the image that gives us the highest confidence score. And how it does that is basically for every image, when you want to generate a new one, you kind of look back and see like what's changed. If something that we changed from the last image made the confidence a lot better, then we want to keep changing that thing in the same way. So like in this case, we give it a face, we see that it's 55.9% sure it's Alice. We generate a new face, and that goes to the model, and it says that now it's 68.4% sure that it's Alice. So we're getting closer. We should keep generating faces, kind of changing those same features to generate new faces. So in practice, this took us less than 2 seconds to reconstruct a face. This is an example from the paper that demonstrates this. The image on the left is a reconstructed image via the model inversion, and the image on the right is the actual image from the training set. So you can kind of see the reconstruction isn't perfect. The image on the left doesn't look exactly like the image on the right. But when researchers gave people the image of the reconstructed face and they asked them to identify what original face it was reconstructing, they were able to do this 95% of the time. So this is definitely leaking substantial information of the training set. So why is this a problem? This isn't as much of a problem if the data is already public, but if it's private, this is a huge problem. If your model is using medical information or sensitive survey questions or pictures of faces that aren't meant to be public, this is a huge problem. And it's a problem for a number of type of models. So some possible defenses. If possible, have the model output less specific information. In the case of the facial recognition network, what researchers did is they rounded the confidence scores that were output. And even with relatively low rounding, the adversary couldn't produce recognizable images. With decision trees, researchers found that if they were split on the more sensitive features lower down, then the adversary couldn't extract those sensitive features. Another thing in general is to anonymize the data. Try to make the data as anonymous as possible when training the model, because even though you're not releasing that training set, it's possible for an adversary to extract. So that's something to keep in mind. This isn't always possible, like with a facial recognition data set. But if designers can do this, then they should try. So the last type of attack that I want to talk about are adversarial examples. And this is when a model is given some input that causes it to give a wrong prediction. This attack is mainly studied in neural networks. So in this example here, we have the original image on the left that the classifier is taken in, and it's classified as a panda with 57.7% confidence. That makes sense. But then what happens is some noise is added, this very small amount of noise, to create the image on the right. If you or I were to look at these two images, they look very similar, but the network is predicting panda for one of them and gibbon for the other. So just that very small amount of noise completely throws off the model. So there are two types of adversarial example attacks. One is digital. So like in the example of the panda, we are modifying the digital data in some way. In this case, adding on noise. Another type are physical perturbations, and this is when the attacker modifies the real world in some way. So for an example, an attacker might place a sticker in a scene that causes the model to produce an incorrect prediction. In this example, we had a classifier that took in images. When it was shown an image of a banana, it predicted it was a banana with high confidence. That's great. But then when a sticker was placed in the scene, this kind of weird looking thing, it now suddenly predicted toaster with really high confidence. So why is this a problem? Beyond AI mistaking pandas for gibbons, this could be a major issue for any system that uses machine learning to make critical decisions. So on the left, we have these glasses that fooled facial recognition, and they allowed someone to impersonate someone else. On the left, we have an example where these stickers and graffiti were placed on stop signs that made it so neural networks weren't able to recognize these as stop signs. And if you have a self-driving car that's using a neural network to make really important decisions, like to stop at a busy intersection, that could be a huge problem. So how does this attack work? How do we generate adversarial input? Not just any perturbation will do. So in that banana example, when a literal picture of a toaster was placed, it still thought it was a banana. But when this kind of weird looking sticker was placed in the scene, then it predicted toaster. So basically what you want to do is you want to use the model and find the smallest perturbation that will incorrectly classify the image while not violating any constraints. And what I mean by that is, like in the stop sign example, the sticker needs to be on the stop sign. We can't put the sticker in the sky. And this ends up being a constrained optimization problem that can basically be solved. So some possible defenses. One is adversarial training. This is where you pretend to be the attacker and you generate a number of adversarial examples and train the network on them so it won't be fooled when it sees them. This isn't very robust. Attackers are going to come up with new attacks. You're going to have to come up with new examples, and the cycle continues. Another possible defense is defensive distillation. So distillation is when the knowledge from a pre-trained network is transferred to a new one. And you can actually use distillation to smooth the model and help the model generalize better to samples outside of its training set. And this is going to make it harder to be fooled by these small perturbations that are used in adversarial examples. I want to wrap up this presentation by talking a bit about the ethical and legal issues surrounding this topic. When it comes to model extraction attacks, machine learning engineers may have to trade off model performance for security. They're going to have to consider if this is a worthy trade-off, especially if that model is being used for critical decisions. Is it worth it to provide that extra security for the model if it means that the model is going to be worse and possibly put people at risk? Legally, there's nothing inherently illegal about querying a model, and yet it's the basis for all of these attacks. We're going to have to consider how to implement laws to police these attacks for the future. Also, machine learning engineers may not feel like they have a responsibility to make sure their input will not fail in the adversarial example situation. In the case of road sign detection, it's already illegal to deface stop signs. Engineers may not feel the need to consider that case because they're already struggling to get models to work on normal output. But failure to deal with these examples could cause an injury and death of customers. Especially with how easy some of these attacks are, it needs to be considered. Thank you so much for watching my presentation. I hope you enjoyed.